We now live in a world where the younger generations are priced out of the market, while almost any avenue to break out of the system is blocked by red tape. Earlier generations lived in a world that they seemingly perceived as too dangerous, so they regulated everything to death over the course of a couple of decades. When young people today want to start their own lives and their own businesses, they will often find out very quickly that the only correct way to do things is so bureaucratic, so expensive, that it might as well be outlawed in the first place. One consequence of this is that the lives of more and more people have shifted into the digital realm. You can't build a home in real life, but you can build a castle in the virtual world. See, I refuse to live in a virtual world, and I seek out places in the real world that you can't explore online. These places are often cold, harsh, and unwelcoming though. Like this scrapyard here, where all kinds of things are hoarded and eventually sold off to be shipped to a foundry, where they will be melted down. This is the last chance for some of these things here to find a new purpose. In these bathtubs over here, we find lots of beaten up old motors and other mixed scrap with partial copper and aluminium content. Many of those motors are nothing unusual at all, but among these things is also this rather whimsical contraption here that oozes DIY charm of a bygone era. It uses a beautiful old Miele brand motor, and this will be the basis for a rather challenging project that we will work on in this episode. Over here I found this collection of work lights that are already loaded into this wheelbarrow here. These lamps are decades old and at first glance in very rough condition. But I'm convinced that a little bit of love will go a long way here and that they will look fantastic once we have put in a little bit of work. And a similar thought had crossed my mind when I was at this warehouse here a few weeks ago. See, this warehouse had been rented by a film production company for years, but now it needed to be cleared out. There were all kinds of things here, leftovers from various projects. Much of it was already claimed by other people, but not this cool old industrial ceiling lamp here that we're also going to have a look at. I also found this rusty old two-jaw puller here, made by the German company Kuko. Also very rusty but very useful are these steel plates that I found on the scrap a while ago. They will come in handy in this episode. On this trip I also found this odd device here, another survivor that can teach us some lessons about the insane lengths that companies had to go to achieve precision back in the day. With all this to work on, let's not waste any time and head over to the workshop. Let's start off with something simple then. This rusty old puller here. It looks like it was left out in the rain for a little too long, and most people would not give it a second glance. In fact, while I was at the scrapyard, somebody saw me holding it in my hand and told me to forget about it. It won't work anymore. Well, we'll see about that. I've already prepared a few liters of concentrated citric acid in this plastic bucket here, and we'll just leave the puller in there while I work on another project, and then much later in this video, let's check up on it again. Let's have a look at this machine then. When I first saw this, I wasn't sure what I would do with it. But as I have said before, I'm just magically drawn to pieces of equipment that were manufactured using methods and materials that would now be deemed too expensive to even consider them for mass production. In this case, I'm talking specifically about the Miele brand motor that is at the heart of this otherwise self-made bench grinder here. It is super dirty, but everything about it is quite unusual and old-fashioned. The motor, the switch, and the plug, even the whimsical way in which the tool rest and guards were braced together is unusual. Right now, you might wonder why I'm even bothering with this. But once we have cleaned everything thoroughly, you will see how beautifully designed this motor is. I have spent many months of this year getting better at casting aluminum parts, and the entire enclosure of this motor is thick cast aluminum, something you never see these days. And since I'm interested in the inner values of this motor as well, I have now pulled it apart completely, cleaning the motor from the inside and inspecting potential damage. But everything here is actually fine. The bushings look good, the rotor doesn't have any signs of overheating, and the stator windings look undamaged as well. But what is the deal with this motor and the brand Miele? The way in which the grinding wheel is attached to the motor looks rather professional, while other parts of this contraption were clearly a DIY project. Well, here is what I have been able to find out. The brand Miele from Gütersloh in Westphalia, actually not far from where I grew up, is well known in Germany for washing machines and other home appliances. Actually, throughout the 20th century, Miele built a name for itself, making extremely long-lived appliances of the highest possible quality. I myself own a Miele dishwasher that I use all the time. It's more than 20 years old. I actually also own one that is more than 50 years old and still in operation, but that's a story for another time. I can't say anything about the stuff they make now though, as I have never owned any Miele equipment made after 2005 or so. It just wasn't necessary. Miele is best known for washing machines though, and sometimes you can find parts of even their oldest models on the scrap, like this galvanized lid here. Old advertisements show, however, that back in the day, Miele also sold electric motors as stand-alone products, emphasizing that there would be almost unlimited use cases for them. Quite a different time and mentality when motors were advertised as consumer products for the home player. But whether they were salvaged from washing machines or bought as parts for DIY projects, they must have been quite popular, as you can still find many of these self-made contraptions on online marketplaces. Actually, I liked this so much that I actually bought a second similar DIY grinder online and had it shipped here. This came with the additional bonus that the second motor actually contained technical information about the motor's pinout. It's a single-phase induction motor with external motor capacitor that can be configured to run on 110 or 220 volts and run in both directions. Truly unlimited possibilities. So here is what I want to do. Instead of simply recreating someone else's DIY project, I will use one of those motors to build my own Miele DIY grinder 70 years later. And here is how I decided to go about this. See, in my last episode I restored this Metabo bench grinder here. After I had already restored the parts that I had actually found, I decided to cast new outer guards for the machine by designing and printing 3D printed casting patterns, making molds from casting sand, and then creating permanent new guards by proper aluminium sand casting. For me, this was a milestone in my own rather recent journey in the world of metal casting. In this episode, I will now up the ante by designing and casting a proper stand for the motor, as well as a guard with adjustable tool rest consisting of an inner and outer component, meaning the task was to first design 3 individual parts in a CAD program, print them out, sand cast them, and where necessary, machine the castings in the milling machine. It will be quite the challenge for myself, but it is the only way to get better at any skill. So over the last 3 years or so, I have used 3D printing and also CNC plasma cutting in almost every video, and in many weeks and months of those years, not a day went by for me where I didn't spend at least an hour with computer-aided design. However, in almost all of my previous videos, I completely skipped the design part and didn't really show any footage of me working with CAD. The reason for that is simple. I've been using commercial CAD software for years, but I was never really all that happy with the programs I used. I often had performance issues on my older computers, and my workflow was anything but smooth, especially when switching between different machines, as I do all the time. I didn't want to show my design work in my videos because I didn't want to involuntarily promote software that I don't even like working with. But a couple of months ago, I was contacted by Onshape, an American company that develops professional CAD software. They were very interested in sponsoring one of my videos and asked me if I would be willing to try Onshape instead. Since the vast majority of sponsorship offers I get don't fit the topic of my videos at all, I was quite happy to try it. At first I was uncertain if I would be able to make a smooth transition, as it is often super hard to change a running system. So the first part that I wanted to design is a pyramid-shaped base that will snugly attach to the motor, fit the overall aesthetics, and also potentially house a capacitor and switch. I first sketched a simple square and extruded that shape to the maximum height I will need. By then using the built-in draft function, this box can be turned into a truncated pyramid by simply setting a draft angle. But the top of the pyramid needs to be round to fit around the motor, and I accomplished this by creating a second sketch on a perpendicular plane. I draw an arc using the 3-point arc feature and type in the correct radius that I had determined while taking measurements of the motor. Together with a line in the top, this arc forms a closed shape that I can select and extrude in order to remove it from the truncated pyramid. Since the plane is in the middle of the part, I have to do this twice. But this part needs to be hollow to be cast properly, also to house components and to make it possible to bolt it to the motor. This can be done by using the shell function, where all we need to do is to select the bottom of the pyramid and specify a wall thickness. In order to be able to bolt the grinder down to a workbench, it also needs a foot of sorts, and that's why I'm now creating yet another sketch, drawing 2 rectangles. And in this way we can create another extrusion that we simply add to the already existing part. When designing parts for sand casting, it's important to have draft angles though, in order to make it possible to remove the pattern from the mold without damaging the sand. An angle as little as 1 or 2 degrees can often be enough. Here I have chosen a larger angle in order to make it more visible in this presentation. Using the fillet function to remove sharp edges is also a good idea when creating a casting pattern like this. The same goes for the inside. I create a draft angle as well as thick fillets. This will help in avoiding sharp and flimsy edges in the casting sand that could easily break. There are no holes visible here in this pattern because I will drill them through the finished casting. That's why they are actually not in the pattern. The 2 components of the guard have a very different form. I already prepared the outer one of those 2 by drawing this shape, mostly using lines and the dimension tool to set angles between lines. The sketch fillet function was used to round off the edges. Using the built-in revolve feature and selecting this line here as our axis, we can create a part that already looks a lot like a guard. After switching to a perpendicular plane, I have now created a new sketch and simply drew a corner rectangle originating in the center of our part, and I used this to basically just subtract 1/4 of our body of revolution. And because I had forgotten this in the first sketch, a draft angle is also added to the inside of the guard. The fillet function is then used yet again to remove sharp edges. So far, what I have shown you here are basically not the real parts, but reenactments of how I made these parts. This, however, is the actual final design and also contains the inner part of the guard that also has a tool rest holder that will be machined after casting. It was more difficult to make, but the general approach was the same as with the outer guard component. Okay, so that was the design part that I have often left out in past videos, and I hope that you enjoyed it. In reality, more CAD and CAM work was needed later in this project to make parts on the CNC plasma cutter. To get this all done, I worked from different computers in this office room as well as in the workshop, as well as on the computers that run my machines, 4 different operating systems on partially outdated computers. In my opinion, this is one of Onshape's greatest strengths though. Since it's browser-based, there are no compatibility issues, no need for updates, and even old computers are good enough to run it smoothly. In the past, I struggled with constant delays and bottlenecks when switching between my different machines, especially when the programs needed to be updated after not using a particular CNC machine for a while. I was really able to get done a lot more by removing all that friction. In my humble opinion, this software can be used for professional projects. If you want to try Onshape yourself, please use my link under this video. If you are curious anyway, maybe just try it. It would help out this channel a lot. If you are an engineer, you can get a professional license for 6 months for free. You don't even have to provide a credit card for that. For everyone else, there is also a free version available. And now, moving on to the more physical part of this undertaking. Okay, so after designing the parts, Slicer software is used to export G-code that tells the 3D printers what to do. When designing casting patterns, you have to compensate for the shrinkage that is going to happen after the molten metal is solidified and cooled down. With aluminium, you typically make the patterns 2% larger than the metal part that you want to create. That can be done in the slicer program in case you forgot about that when designing the part. In the meantime, I had figured out that I would most probably require larger, more professional casting flasks to complete this project. But I couldn't wait to get started, and that's why I first tried to cast a new base in this rather improvised flask here that I had also used in my last video. To cut a long story short, a few months ago I was experimenting with making molds from steel rather than sand, and I'm still interested in that idea. However, I also remember that one of my friends, his name is Dennis, worked as a sculptor for many years, and he made a lot of bronze castings in his old job back in his home country of Bulgaria. He wanted to visit me at the shop to show me some sand casting techniques, so I hurriedly slapped together a few pieces of wood so that we could just get started once he arrived. We really spent a fun afternoon together, and he showed me the techniques that he and his friends worked with. We only made very crude aluminium castings that day, but I was super happy and thankful about his advice and enthusiasm. Over the next few days and weeks, I used the same improvised flask over and over again to experiment with different patterns, until I eventually used it to make the guards for the Metabo grinder in the last episode. So after I had already filled the lower part of the mold, called drag, with casting sand, I started to prepare the pattern by applying talcum powder to its surfaces. This will later help in removing the pattern from the sand, which might otherwise stick to it. And then I fill the hollow bottom of the pattern with sand, by first putting the sand through a riddle and then compacting it using a rammer. After striking it off, I place the pattern on top of the drag and apply pressure so that the sand core will kind of fuse with the larger body of casting sand beneath it. I then lift the pattern up to see if I can get it loose. And after that, I clean and rework the sand where it is necessary. Then the pattern is rather loosely lifted back onto the mold, and more talcum is applied on the top surface and along the entire parting line. The upper part of the mold, called cope, is now placed onto the drag and fastened in place. This is one of the many weaknesses of this improvised flask. Cope and drag can easily slip and lose alignment, ruining the cast, especially when removing the flask from the bench. So the riddle is again used to fill this upper section of the mold with fine sand before it is carefully compressed by hand. With an at least 2 cm thick layer of riddle sand over all surfaces of the pattern, the uppermost layers can be coarser chunks of sand that can be put into the flask by hand. In the end, everything is rammed and a strike bar is used to create an even surface. The cope is then carefully lifted off and placed next to the drag. The pattern is removed, loose sand is brushed or blown aside, and smaller damage is reworked. And then I cut a sprue and vents into one side of the cope. This is where the metal will be filled into the mold and where gases can escape. Risers will also automatically form here that can feed the casting if needed. Cope and drag are then rejoined in an upright position, and clamps are then used to fasten the two halves together. Note that an imprecise and improvised setup like this will hardly allow you to achieve the same alignment of the two parts that you had just a few minutes ago when forming the mold in the first place. So after lifting the flask to the ground, we can now pour molten aluminium into it and wait for it to cool down. At first glance, it actually doesn't look that bad. Unfortunately, after turning the casting around, you can see that one wall of the pyramid is missing. While handling the flask and or rejoining the halves, I must have misaligned them, or a piece of the sand fell off, hard to say. In a similar attempt, I also tried to cast an earlier draft of the larger of the two guard components in this flask, but it simply wasn't up to the task. We need to build better casting equipment to finish this job. So let's do that then using scrap metal. Okay, I'm interested in a long-term investment here. I don't want a quick fix, but a variety of flasks of different sizes that allow me to work on future projects without running into the same issue over and over again. That's why I'm now making 4 different flasks at different shapes and sizes that should help me to overcome the old problems. Let's start with the smaller ones. They are not made from scrap but from new flat stock. After measuring and marking, I'm using this saw here to cut the stock into pieces. I fixed that saw in another Scrapyard episode some years ago, by the way. All in all, I cut out 8 sections and I have arranged 4 of them into a rectangular pattern now. While they're being held together by a bunch of clamps, I use my TIG welder to first weld a few tacks before welding all the sections together permanently. It's nice to work with new material for once, by the way. Who would have thought that there is such a thing as steel that's not covered in rust? So this is what the bare frames for the first flask look like. I tagged cope and drag together temporarily to make sure that they fit onto each other perfectly. But this is just the most basic part of the work. In a few minutes I will show you some improvements that will take care of my alignment and clamping issues as well. But these 2 smaller flasks will not be much bigger than the wooden one I used so far, and that's why I also wanted to make 2 much bigger ones, and for that I'm going to use material from these old steel plates from the scrap. Unfortunately, it was quite a lot of work to prepare these pieces to be cut and welded, but the alternative would have been to buy new material, and for steel plates of this type and size and shape I now would have to pay somewhere around 300 euros or more. It's insane. So a lot of preparatory work was involved. This part here still had other pieces of steel welded to its surface that I needed to cut off before going on to sand off a thick layer of ancient rust. The second one was from a set of plates that I brought home from the scrap years ago. And frankly, I would now probably tell myself in 2019 or whenever that was to leave them where they are. They have this pattern on one side that I believe could be helpful for the flasks because the sand has something to cling on to, but getting the nasty old paint out of those indentations was a nightmare and it consumed large amounts of paint stripper. I used my garbage bag method again, where the paint stripper works inside the garbage bag to keep it moist before the bag is then reused to hold the nasty sludge you are left with after the stripper has done its work. This piece of steel would now cost 100 euros or so. It's almost new and has this plastic-like coating. I applied paint stripper once again. And while I waited for the stripper to do its thing, I have also designed and printed these parts here that will help me to improve my approach even further, as you will see in a few minutes. Fortunately, it didn't take all that long in this case and the coating was a dream to get rid of. So after I had prepared the steel as good as I could, the pieces were placed onto my CNC plasma table that I built last year, and I cut out various pieces for 2 differently shaped, rather large and heavy casting flasks. One of them will have round openings on one side that will allow me to use it both lying down as well as standing upright, like the wooden one I used before earlier in the video. Just like the flat stock before, all these parts were welded together so that I ended up with a basis for 4 flasks. The advantages of the improvised wooden one are so far that they can't catch fire and that they are more precisely made and have a tighter fit. However, a few additional improvements were needed to assure better alignment and to make screw clamps obsolete. So what I did next was to cut angle pieces into sections and tack them together. Holes were then drilled, and I also cut a few threads. The angle pieces were then welded to the frames, sitting exactly over the parting line between cope and drag. The tack welds were then cut open again. In addition, I also welded these upside down angles into the sides of the smaller frames to give the sand something to hold on to. That might not be strictly necessary, but it won't hurt either. As you can see here, the 2 halves now just snap together using the outer two bolts as pins, while the bolts in the center hole can be used to screw the two halves together using a set of M6 nuts. And I have now added this feature to all of my flasks, and they are now ready to be used. In the meantime, I had also found the time to print out the final designs for the guard patterns. Contrary to popular belief, 3D printing isn't an easy solution for any possible shape or form. In reality, there are lots of constraints to work around. When making hollow parts like these, for example, there is always going to be support structures that will create waste and also a rougher surface on one side of the print. I oriented the parts to face upright with that side that will be more visible from the outside, to achieve a fine structure where it is actually visible. With all this done, it was time to have a second attempt at casting these parts. So the process starts anew. The drag of our new rectangular flask was already filled, rammed and struck off so that the cope could be placed on top of it to be bolted down. And since we will now use the flask lying down instead of standing upright, these 3D printed cone-shaped parts will be used to form a sprue and risers instead of the other method where I simply cut those features into one half of the mold. Other than that, it is exactly the same process as before, where the cope is filled with sand before the halves are separated to remove the pattern again. And after doing just that, the two halves are bolted together again and the placeholders are removed. Meanwhile, I also ordered this granulate. It is mixed into our cast aluminum and stirred in order to remove impurities. By the way, I'm only using aluminum alloys that are specifically suited for casting, essentially by recycling parts that are already made out of cast aluminum. After the material has been poured into the form, we'll leave it there to cool down. In fact, let me walk you through the casting process for all three parts before actually revealing and inspecting the results. The second cast will be the outer part of the guard. For this pattern I chose the square-shaped flask, and the process is basically the same as with the base before. But with the third and final part, it gets a little more suspenseful as we'll use the big flask for the first time. I've seen that they use hoists and overhead cranes to lift and move their molds in big foundries, and I think for the next project I will do that as well. The sand was then sculpted in such a way as to complete the overall shape of the pattern, so that it could be removed later without any friction. And after filling the cope with a ton of sand, and again carefully placing sprue and risers, it is then lifted off, which I barely managed without damaging anything. You couldn't make it much bigger before indeed having to use a hoist. So I remove the pattern and inspect both halves of the mold, and repair whatever little damage I might have caused in the process. So we cast the second guard component and wait for everything to cool down. Moment of truth. And I'm happy to say that all three parts turned out great. Spruce risers and smaller unwanted irregularities were cut and ground off, and the surfaces were cleaned and brushed. And this is what our parts look like now. After that, only a few more steps were needed to assemble these parts. 3 holes had been drilled into the guard, and new threaded rods were needed to bolt the guard to the motor. Additional holes were also drilled into the base and motor housing, and a few threads were cut in order to connect these parts and also bolt down the grinder to a workbench. It was a moment of pure joy to see all the components put together. The tool rest itself will simply be welded from 2 pieces of steel, like on the Metabo grinder. But in order to fasten and adjust the position of the tool rest, we still need to cut a slot into this casting, and I did that on my milling machine. We could have tried to create this slot while casting the part, but it would have been hard to do without draft angles, and I don't want any draft angles here in this slot. And this is what the grinder now looks like with the tool rest in place. All that remains to do is to install a switch and a capacitor into the base. However, I simply could not yet decide what style of switch to install. So that was my take on the Miele grinder 70 years later. What do you think? Do you like how it turned out? Well, I like it a lot. In fact, since I have 2 of those motors and with the patterns in place and workflow established, I have started to make a second one. Maybe I will make more of them if I manage to find more of these old motors in the future. The only problem is now that it's looking a little too good to be used for actual work. But what happened with that bearing puller? Well, since the acid was rather strong, the temperature mild and rust aplenty, it started to turn yellow very quickly as iron citrate complexes are created. Over 1 or 2 days, the liquid turns into a darker and darker yellowish brown. The workpiece can now be rinsed off and already looks completely different. Since the screw is stuck, an impact is used to break it loose. And because there is still rust on that little part the acid couldn't reach, it goes back into the solution for a few hours. After that, I usually dry the piece with a towel and put it next to the oven or in the direct sunlight depending on the time of year. I then spray it with ballastol or another long-lasting film-forming oil. And there it is, next to its little brother. Nothing spectacular, but it's a high-quality tool that will come in handy sooner or later. Another find that I wanted to talk about are these work lights here. They were made in the 1990s by a German company called Indulux. They look pretty rough, but I really just like their shape and thought that they would have great decorative value even if it turns out that they wouldn't be used as work lights anymore. So what I basically do here is to take them all apart completely, clean everything, and get a general idea of their quality and see how they were made. And in a way, it felt once again like time traveling. The lamps are still equipped with extra rugged incandescent light bulbs made in Germany. These are special versions for rough environments. But in general, I still remember the days very well when incandescent lamps were the standard. And back when they were phased out, I didn't really care since we seemed to head for a better, more efficient future. But I didn't realize back then that many of the parts that would go into our modern LED lamps were just very low quality. Sitting here, looking at an extra rugged light bulb made here in this country, I thought to myself, well, we'll never see this again, and it felt a little sad. You will laugh at me, but I really tried to get these parts clean again, at least as far as that was possible. The old rubber parts still feel really sturdy, but they look horrible. Some people might think to spray them with oil might be a good idea, but you shouldn't do that. It'll make the rubber brittle. Silicone spray, however, you can use. The rubber will look completely different. I can attest to the fact that this is a long-lasting effect that doesn't seem to harm the rubber. That was at least my experience over the past few years. Unfortunately, the lamps were all missing their power cables, and I wouldn't buy new ones for old lamps like these. However, while I was at that TV production warehouse, I also found this box of tangled up wires here, and that will save the day. While I went through this mess here, I wondered if the company Indulux was still around. And I found a newspaper article from 2015 reporting that the company Erso Indolux was closing shop after having manufactured working lamps since 1952. The 73-year-old second-generation owner of the company was interviewed, and in that interview he is clearly heartbroken that his life's work is vanishing before his eyes. The reason he cited were that craftsmen would now buy their lamps online, and that their lamps weren't suited to be used with LEDs. It's a sad read, and looking at this from 10 years later, I have to admit that things really have changed a lot. While it is no problem at all to find new powerful LED replacements for the old light bulbs, and that is exactly what I did here, I do have to admit that since we have now mostly switched to work lamps with no replaceable permanently installed LED modules, building a lamp like this in today's world would seem like an anachronism. I even went as far as polishing some of the lamps, at least those where it still seemed to make some sense. 3 of them were so dull that they couldn't be saved, but I had another idea. I painted them red so that they could be used as alarm indicators, like with my furnace here. After all this, the lamps have new LED replacement bulbs and power cables, and I think that they look really cool. A related find was this old industrial ceiling lamp or luminary here. It was made by Siemens in the 1960s. It is super disgusting though. I think it was used in a kitchen as it's covered in thick grease. In order to get that off, I had to employ the steam cleaner. This style of lamp was used in many factories and industrial warehouses in Germany back in the day. Everything about it is super high quality and heavy, like this cast iron enclosure here. After lifting off this sheet metal hood here, you can see why the lamp has this shape. Many people think that these lamps are super cool, but don't know how to use them with modern LEDs. The reason is what you see here. What some people might mistake for a transformer is actually a ballast choke. And there is an Edison-style socket here, type E40, built into the lamp, and some people might think that that's where a normal incandescent light bulb is supposed to be screwed in. But incandescent light bulbs are actually terribly inefficient. They are actually more like heating elements that also happen to emit some light. In industrial settings, where a lot of light was needed, discharge lamps were used instead. Back in the day, those would have been mostly mercury vapor and sodium lamps, as you might know them from streetlights. Those require a ballast to limit the current flowing through the lamp, which would otherwise destroy itself. Long story short, if you just want to use these lamps with modern LED bulbs, you can simply remove the ballast and capacitor and just connect the socket directly to the mains. And for demonstration purposes, I have now installed the lamp on my ceiling temporarily, and I really like its industrial charm. I had actually also planned to have a look inside this interesting contraption here today, but the video has already been much more work than I had planned for, and that's why we're going to have a look at this specimen in the next episode. So I hope that you liked the projects that I had in store for you today, and if you want to see more Scrapyard videos, please give it a like. It would mean a lot to me. 2 ways to support this channel and keep it alive and kicking is to make a donation. A link for that is under the video. Or maybe give Onshape a try and use my link. If you are curious about it anyway, or maybe just want to try to make your own parts, just try it out. It would really go a long way in ensuring a future for this insanely work-intensive undertaking that I call my life. Furthermore, there is also the option of becoming a supporter of this channel on Patreon under patreon.com/tpai. See you soon.